So, all right, we're back for this meeting of gauge theory virtual. We are pleased to have Cliff Taubes. He's going to tell us about eigenvalues on the two sphere, which is a fun thing. I will let him take it away, and I'll turn off my ugly mug.
Well, thanks for asking me to speak. It's always a pleasure. So this is joint work with Yinging Wu. That's what I'm going to talk about. So let me just remind you what the Laplacian on the two-sphere is. So there actually is a little bit of gauge theory here. So I will get to the gauge theory at some point for about 20 seconds. But anyway, so I hope you forgive me for only spending 20 seconds on gauge theory, although the whole talk can be thought of as Z2 gauge theory. Okay, so we're going to talk about the round sphere. So here's a sphere. It's got the round metric. We think of it in R3 as a sphere of radius 1. And we can take, the usual, whatever you call them, spherical coordinates, theta and phi. So theta is that angle and phi is this angle. And then the Laplacian is just the usual spherical Laplacian. It's sort of 1 over sine theta, d by d theta. And then there's the two derivatives in the phi direction. So basically everything you've ever wanted to know about the Laplacian and its spectrum and its eigenvalues was long time ago. I don't know when, probably, I don't know, 1800s, 1700s. Anyway, it's been known forever. It has discrete spectrum and what is its spectrum? The spectrum has the form n times n plus 1, where n is an integer. Those are the eigenvalues. Well, if I take minus the Laplacian, those are the eigenvalues. N is an integer. N goes 0, 1, and so on. And the multiplicity of eigenvalue n is 2n plus 1. And in fact, the eigenvalue, eigenvectors are the usual spherical harmonics. Spherical harmonics. And if you actually wanted to write out the eigenvectors and you don't want to deal with spherical harmonics, what you can do is take a degree n polynomial in the coordinates I1 on R3, and but it should be traceless under all possible traces here, and that's a harmonic function. So what you're dealing with, you take a homogeneous harmonic function on R3, harmonic function on R3, and you just restrict it to the unit sphere, and that restriction will be an eigenvalue of degree. If this is an n, I think it'll be degree n. It'll be the number, have energy. That'll be its energy. So that's the story. And then, okay, so there are all kinds of cool analysis and everything, but I'm not going to talk about that. But then it turns out there's another eigenvalue problem, actually a whole family of them for the Laplacian on the sphere. So this is our Laplacian here. Okay, so there's a whole family of these guys, and how they differ from the standard one is that the domain of the Laplacian is different. So now let me describe what I'll call the Z2 Laplacian, or Z mod 2Z Laplacian. So this is, okay, so if you like, it's gauge theory for the group Z mod 2Z. And here's what you do. we'll take the round sphere again. And what you do is you fix a configuration of two n points. So take n to be an integer, different n than over there. So here's 6 points. So you set a configuration of two endpoints on the sphere. So I'm going to call it configuration P. And now look on the complement of the points you've chosen. So look at S2 minus P. And what you want to do is look, and now this complement has a kind of canonical line bundle over it. So sitting over the complement is a line bundle we'll call I sub P. And how that line bundle is defined is if you go around any one of those points, it's a real line bundle. If you go around any of the points, the monodromy is -1 going around the points. Okay, so that's our real line bundle. And in fact, that's why we have to have an even number of points, because you couldn't do that without an even number of points. So that's our real line bundle. And now, well, I'm going to think of it as having a fiber metric, but really, I think of I have a fiber metric, or alternately, I can think of it as that there's a degree 2 cover branched over the configurations. And this is, which I think of as a principal Z2 bundle. And this is the associated real line bundle. So, so I can look at the Laplacian that I just wrote down. I can consider minus Laplacian acting on sections of this bundle. Okay, so sections of the bundle aren't actually defined over the points, but they are defined on away from the points. And actually, I'm going to consider sections which have the property that the integral of the df squared is finite. So that's my space of sections, less than infinity. Okay, so if I think of it acting on there, then I can make sense of an eigenvalue and eigenvector. So it's the same idea. F is an eigenvector if it satisfies this equation, and then lambda is the eigenvalue. Okay, and so then you can prove a whole lot of nice theorems about this. So for example, even though F is defined on the complement of the, is only defined on the complement of the points, it turns out that the norm of F goes to 0 as you approach the points, as configurations are approached. Is approached, and in fact, what you can do is there's actually kind of a Taylor's expansion near a point. So suppose I have a point X in the configuration, then F near there has a kind of a Taylor's expansion, which is this. It looks like the real part of a complex number, we'll call it AX, time. Now, let me just set my coordinates here. I take stereographic projection. So I think of the coordinate, I have a complex coordinate, we'll call it Z. So it's a real part of the square root of Z plus O of Z to the 3/2. And this AX is some complex number. And if AX actually were 0, then F would go like the real part of some, we'll call it A1X times Z to the 3/2, and so on. So you can prove all kinds of cool things. In fact, it has a whole, sort of power series, but the power series is in half odd integer powers of the square root of Z. And the reason for that is is that when you go around these points, you have to pick up a -1 when you go around the point. So it has to be it has to have this two-valued property. So that's what they look like. And so what about the eigenvalues? Well, you can go through the sort of standard proofs of these things, and you see that the eigenvalues form a discrete set. Eigenvalues form a discrete set. The discrete set is in, so it's discrete and finite multiplicity, discrete finite multiplicity. And no accumulation points. Okay, and the eigenvectors are complete, they're complete orthonormal basis. Well, you have to orthonormalize them, but anyway, it's a complete basis in a suitable sense. And so, it's always the same story. And so what we were interested in is how do the eigenvalues and eigenvectors vary? How do eigenvalues and eigenvectors vary with changing the configuration? So what happens if you start moving the points around? What happens to the eigenvalues and what happens to the eigenvectors? So you start moving the points, start with the points here, and then we start moving them. What happens? So let me tell you why we're interested in this. You see, so here's where the gauge theory comes in. So this is it's just like for the standard Laplacian. If I have an eigenvector, then I get a homogeneous harmonic one form, homogeneous harmonic one form on R3 from this. And what you do is you take R, the radial direction, I forget if it's R to the lambda or some number alpha, which depends on lambda. I forget what it is. But you take D of this, and so this is turns out to be a harmonic Z2 valued function on R3. And this is what is it, zero locus? Let me write that out. This is alpha R to the alpha minus 1 dr times F. Plus R to the alpha df. So it vanishes. It vanishes where df and f are both 0. So if we want a Z2 harmonic one form, homogeneous on R2, we need df and f both to vanish at the same place. Okay, so we're looking for f's, which are eigenvectors for some configuration, where df equals 0, where f does. so the zero, so if you think about what we're doing here on the sphere, remember that I said near these points, it has an expansion like the real part of AX times the square root of Z. We're looking for things where AX is 0 for all X. Those give us, if AX isn't 0, then DF actually blows up like 1 over the square root of Z. But if it is 0, then DF goes to 0 at the same place where F is 0. So what we're getting here is if we can find an F, an eigenvector, for some configuration where the AX is 0, then when we look at what's happening on R3, we're getting a homogeneous harmonic 1 form whose 0 locus is a union of rays through the origin, which are the rays through these points. Oops, didn't mean that. And so now why are those interesting? Well, now here comes the gauge theory. There's various gauge theory equations in dimension 3 that are sort of, generalizations of the Seiberg-Witten equations. Generalized Seiberg-Witten equations, or SL2C flat connections are another kind of gauge theory where we have SL2C curvature, some F equals 0 for SL2C. But anyway, there are these generalized kind of Seiberg-Witten or, Chern-Simons gauge theories where you have more than one spinner in the Seiberg-Witten case. So this was studied by Thomas Wapolsky and blanking on, anyway, I'm blanking on his name. I'm getting old. I don't remember names anymore. Yeah, I know him well. I mean, we were offices across the hall all last year. Anyway, so these typically have non-compact moduli spaces, and there's a kind of a compactification of the moduli space, which is defined. So these take place on a 3 manifold, and the moduli spaces have a compactification, which is characterized in part by something which has Hausdorff dimension 1. So my student Boyu Zhang studied this, and so it's a closed set with Hausdorff dimension 1, and then there's a line bundle I over the complement of this thing, M minus Z, and then there's a harmonic 1 form or harmonic spinner defined on the complement of, so I'll think of 1 form dV and d star V defined on the complement, which has values in this line bundle and vanishes along Z. So the non-compactness is sort of is characterized in part by this data consisting of the closed set Z, the line bundle I, and this harmonic 1 form or spinner. And but Z could have singularities. So Z might be quite sort of bizarre looking. But if you take a singular point and you dilate in sort of Gaussian coordinates, so you sort of take Gaussian coordinates and you just blow up, then if you rescale in the appropriate way, you get a limit on R3, and that limit on R3 is exactly one of these guys. Okay, so my motivation for studying this problem was to see about finding singularity models for the behavior near the set Z. Okay, so that's where this problem comes from in the gauge theory side. Anyway, so what we would be looking for is a configuration P in S2. So this is so configuration P determines the rays through the origin in R3, and then we're looking for a harmonic function, harmonic section of that line bundle IP. And we want the function f to vanish like z to the 3/2 near each point in P. So that's what we're looking for. Now, so the question is, are there any? Well, you can do the case almost everything you need to know. You can do the case where there's 2 points, so just 2 points in P. Well, everything's rotationally invariant, so I'm going to take one point to be the South Pole. I hope my friends in New Zealand and Australia will forgive me for that, but anyway. And then you can take the other point and you can move it around. And from the point of view of the eigenvalues and spectra, it doesn't matter. The angle doesn't matter. It's just the distance between the 2 points. And what you can show is that the f's, all the eigenfunctions go like the square root of z near the 2 points, except when you get up antipodally. Okay, so when you get to the antipodal point, then you get some interesting behavior where you have actually actual solutions. So when you're antipodal, you can write out the eigenvectors and eigenvalues explicitly. And for example, these would be sine to the n over 2 theta, and then the real and imaginary parts of e to the phi. Oops. E to the n phi over 2. So this is multiplicity 2, and then you get more of these by rotations. The generator of rotation, you can, if you act by the generators of the rotations. Of course, generate rotations around that direction doesn't do anything, but if you rotate around some point on the equator, then those generate a whole sequence of these. And so what happens is that you get multiplicity 2n for the eigenvalue, and for these lambda is n squared minus 1 over n squared minus a quarter. And so this one, so these vanish order n over 2. Right, so if n is bigger than a half, you have solutions that we want, and so you have lots of them, but they're all antipodal, so that's not very useful for finding singularity models, because the antipodal case occurs where the set Z is actually a C1 submanifold, so we don't care about those. And then Ying Wu and I found other examples where n equals 4, where you take the vertices to be the, you take these guys to be the vertices of a regular tetrahedron inscribed in the, inside the sphere. And then we can use the symmetries of the tetrahedron to find examples where there are 4 points, and then we can do the other Platonic solids also. And I think we got up to 12 points. But unfortunately, we ran out of Platonic solids, so we only get 12 points. So the question we wanted to know is, well, are there singularities which have the desired behavior that f goes faster than z to the 3/2 near each point? for higher n bigger than 12. Okay, so can we find them? So that sort of was our motivation. Okay, so the question is, how could you do that? How to do that? So it turns out the problem can be reinterpreted in an interesting way. So let me explain that. Well, let me explain a little bit of a mystery first. So here's the mystery. So first of all, the smallest eigenvalue, if I fix a configuration of some number, even number of points, then we can associate to that configuration the smallest eigenvalue. I'll call that E of P, the smallest. And so E of P is always positive. And the reason is this, the reason is that, you know, if the thing goes like, if it goes like square, the thing is a little bit of, if you take a little circle around any one of these points, the line bundle IP is the Hopf bundle on one of these, is whatever, Mobius bundle, not Hopf bundle, Mobius. And now the eigenfunction f is in a section of the Mobius bundle on that point, on that little circle. So in particular, the integral of df along the circle, we'll call it df. This can't be zero because it can't be constant, right? Because the Mobius bundle doesn't have any constant sections. So on each little linking circle, in fact, this is greater than 1 over r squared, or rho squared, times the integral f squared along a circle C, where rho is the radius of the circle. This is rho. So that makes the energy has to be positive. Okay. So what you could do is say, well, so we now can define a function on our configuration space, which is this lowest eigenvalue. We can say, okay, well, let's look at this function. And we can, for example, look at its maximum or minima. Those should be critical points, right? So what about the minima? Well, it turns out that the infimum of E is always 0. So look, and what does the infimum look like? Well, what you're doing when you go to the infimum is, if you take all of the points, all of your points, and you put them really close together, then the infimum, the eigenvector for that looks a lot like, so the bundle you're looking at has 0 monodromy when you go around all the points. So out here, the bundle is a trivial bundle. It's just a product R bundle. And well, the minimum eigenvector for the product R Laplacian is just a constant one. It's just a constant function. So these guys become constant out here, and their eigenvalue is nearly 0. So you can show the infimum is 0. In fact, there's a compactification of C2n. So I define this minimum function. There's a compactification of C2n, which is, I'll call C bar 2n, which looks like C2n. And then what happens is, in this is 2 points come together, you get this. And then you can have either 2 pairs of points coming together or 4 points coming together. And then the last one is you have all the points coming together. We'll call that C0. So what happens in the compactification is this subspace. This subspace, you have 2 of the points. 2 of the points are really close and coming together, and then the other points aren't so close together.
Cliff?
Yeah.
So I'm just slightly confused by this compactification, because somehow I would have thought if you have 2 points coming together, do they you just throw them out? Because it sort of looks like 2n minus 1 points. I know that's not the right
Oh,
setting for your
you,
problem.
you have to throw them out because when they come together, there's no monodromy around any little circle where they came together. So the bundle becomes the trivial.
So it's not like the monodromy around that.
Yeah,
some new
monodromy.
point that's of
Yeah.
even order or something like that.
Yeah, see the monodromy when they come together here is just +1. The only way to get -1 is to go between the two of them, but if they come together, you can't do that. So the compactification means you have to throw out even numbers of points that come together. And if odd number of points come together, you keep it as 1 point.
Okay, thanks.
So that's the idea. Anytime if even numbers cluster, you throw out any even number cluster, and any odd number cluster you replace by 1. So that's how it works.
Okay, thanks.
Yeah. So another way to get this this thing, I said even you could have 2 come together. You can also have 3 come together to get here, and then you're left with 1. Okay, but you can never get an odd number in the compactification. So anyway, so that's our compactification, and so so you can think of it actually as a quotient of the compactification you described. It's a quotient where you throw out points. You think of it as a divisor. You think of the configuration of points as a divisor, and then you're throwing out all the even divisors and just keeping the odd divisor. So it's kind of what I would call a Z mod 2 divisor. That's really a compactification. Okay, anyway, the basic limit is that this E extends over the compactification continuously. And now what you can show, so as I said, the infimum of E is 0. So therefore, looking for the critical point, but to be the minimum isn't going to do you any good. Okay, because you're just going to get, your critical point will be in the compactification will be on the divisor where there's no points left. So then you can look at the supremum of E. So that's maybe a better idea. And what you find is that, first of all, the supremum of E on C2n is going to be bigger than the supremum of E on the lower strata. So that tells you that it has to be on any lower strata. And in fact, what you can show is that it in fact grows like a constant, some small number, faster than some fixed number. We'll call it 1 over C times n. So you actually have a chance of finding a critical point. Well, a place. Oh, I didn't explain what this has to do with critical points. Silly me, I missed something important. Yeah, I'll say this, why this is relevant. You guys let me get away with that. We define E, so here's a, right, well, let me finish this first. So E, let me explain why we're interested in this. E grows like 1n. If it takes on its maximum, it takes on its maximum inside C2n. What does a configuration look like? Well, the configuration looks like having the 2n points more or less evenly distributed over the sphere, because then there's a roughly the same distance between them, and oops, they have 5 points, need 6. And any eigenfunction has to vanish on circles, on every circle that crosses an odd number of these, you might call it a Seifert surface for the configuration, but it has to cross, if it crosses an odd number of times, it has to vanish, and that forces you to have roughly an n's worth of energy from that. So why are we interested in critical points? Well, here's a theorem, here's a proposition. So this is why we're interested in the proposition. Proposition is that an eigenvalue doesn't have to be an eigenvalue that defines a smooth function on a neighborhood of any configuration of P if it has multiplicity 1 at P. Okay, so that's the first statement. So what is that saying? That's saying if it has multiplicity 1 at a configuration P, if you move the configuration, it has to stay having multiplicity 1. And so there's a well-defined way of associating the eigenvalue at P with nearby eigenvalues, and that moves smoothly. So that's just perturbation theory. That if you say, let me try to find, let's look at the lowest eigenvalue as a function of configuration, wherever that lowest eigenvalue has multiplicity 1, then the eigenvector changes smoothly as you change P. It's sort of a Kurenishi picture, if you like. And therefore the eigenvalue changes smoothly and it's a smooth function. So any eigenvalue defines a smooth function where it has multiplicity 1. Now, if it has multiplicity bigger than 1, it might not be smooth there, because if you move off, if it has, say, multiplicity 2 for a configuration, then there are two eigenvectors with the same multiplicity. And as you move away from that configuration, one might go up and one might go down if you move in one direction. But if you move in the other direction, one might go down. They might change which goes up and which goes down, and then you couldn't, smoothly fix that eigenvalue, choose the eigenvalue to be smooth as you cross through that multiplicity configuration. Any questions? You guys following this, or are you guys lost? Anybody lost yet?
I'm gonna confess that I was lost. I didn't understand that proposition.
Oh, the proposition.
Or maybe just maybe I'm just sort of missing the.
Yeah, the proposition is saying that, suppose we said, I want to consider like the second highest eigenvalue as a function on a configuration space. Mm-hmm. Okay, it says that function is smooth near any, in a neighborhood of any configuration where it has multiplicity 1.
But what do you mean by the multiplicity?
I mean, if there's just one, if the eigenspace is one-dimensional.
Oh, okay.
If the eigenspace is one-dimensional for the second eigenvalue, then nearby it stays one-dimensional, and the eigenvalue itself moves smoothly with as you move the configuration.
So you're saying if it had you could have some sort of splitting of the eigenspace, right, otherwise, and that would be sort of non-smooth behavior.
Right. So if the eigenvalue happened to have, if the eigenvalue, the eigenspace has dimension bigger than 1, then the eigenvalue won't be smooth across. It won't be differentiable. It'll be continuous, but it won't be differentiable across when you hit that configuration, because their different directions might split the eigenspace in different ways. And actually, that's what happens. So, for example, if we're looking at the minimum eigenvalue, that actually is a smooth function as long as the eigenspace is one-dimensional. Okay. And so why are we interested in that? Well, then there's part 2 of this proposition. Part two says that where the eigenvalue is smooth, where it is smooth, which is to say the rank of the eigenspace, the dimension, is equal to 1, this function configuration mapping to lambda of p is a critical point. If and only if all the AXs, well, if and only if all those AXs are 0. So if and only if the that one is a one-dimensional eigenspace, f goes as z to the 3/2 near each point in near each x in the configuration. So it's precisely the critical points so we reinterpreted our problem, at least in part, by saying if we can find if this function is smooth where it has its maximum, if it has a dimension 1, the eigenspace, then it obeys the condition we want to give us one of these harmonic 1 forms on R3. So our condition of the vanishing at higher order near each point is exactly the same condition as saying that the eigenvalue is a critical point of Okay, so that sort of motivates our looking at this as a Morse theory problem, because then we can attempt to use Morse theory to find the critical points we're looking for.
Cliff, just to remind myself of back to the gauge theory picture. In the setting of the gauge theory picture, no matter how many points, you always want your f's to decay as z to the 3/2
or higher. But see, if the gauge theory picture, let me go back here. Where is it? I forget where I had it. Oh, all right. Well, I'll write it over here. In the gauge theory picture, if I have a f on S2 obeying lambda f, then the harmonic 1 form is, there's some alpha which depends on the lambda. I forget the formula, but anyway, it's sort of r to the alpha minus 1 f times dr plus r to the alpha df. And so we want this, so if this is v, we want v to go to 0 on our set z, on the rays through the origin. Okay. Well, the only way it's going to go to 0 is if both f goes to 0 and df goes to 0. Because these can't cancel. This is derivative in the r direction. That's derivative in the spherical direction. Well, f goes to 0 because f goes like z to some power, odd power. Df will go to 0 if n is bigger than 1/2. Otherwise, df blows up. Otherwise, df goes like 1 over the square root of z, which actually blows up. So we don't get what we want. So we can't use the generic f for generic configuration p goes like z to the 1/2 at least one of these points, and so we can't use it. We have to find those special configurations which have f's that at each of the points goes at least like z to the 3/2. And those are exactly the critical points for this function. Okay, so
the critical points can go as z to the 5/2 then. It need not have a leading order of 1. Leading order of
z to the 5/2 is fine. We don't care. We just can't have z to the 1/2.
So near the points so the coefficient of the zeta 1/2 is sort of like, gives you a coordinate on, gives you coordinates on this configuration space.
Right.
Near, and you magically this P has a nice, the eigenvalue has a nice expansion in terms of those coordinates.
No, the differential does.
The differential does.
Yeah, so so remember, what is the tangent space to the configuration space at some configuration? Say the configuration is x1 up to x2n. The tangent space is a set of vectors that are tangent to these points in the sphere, right? So we have two endpoints in the sphere, and the tangent space to that configuration is just a set of vectors at each point. And now I can tell you what, I can write the differential in terms of these vectors. So the differential of the eigenvalue is some expression in terms of these vectors. That has to localize. These vectors are at these points, so you might hope that the expression localizes to an expression at those points. And in fact, I'm trying to remember the formula, but it's something like up to some factor like 1/pi, it's the sum over the points. And then you take the metric inner product between the Vx and then the real part of Ax squared. So I think of, I can interpret Ax as a square root of a vector, and Ax squared is a complex vector, and you take the real part of that. It has to be the square because anyway, because Ax is only defined up to plus or minus 1. So it's like this, and so if this is 0 for all Vx, then you have the Ax squared equals 0 at each x, so Ax equals 0. So there's a cool formula that computes the that computes the gradient of the eigenvalue in terms of it just localizes it right at the points. So and that's sort of the key to this observation. And actually, if the eigenvalue has degeneracy, there's a generalization of this formula, but it doesn't appear to be too useful yet. Okay, more questions. Okay, anybody lost still? It's okay to be lost. You know, after doing mathematics for a long time, I've come to the conclusion that the key to becoming a successful mathematician is getting used to being lost all the time. Okay, so that's the primary prerequisite. People who are uncomfortable being lost don't make good mathematicians. All right, so we're looking for critical points. So now we have an interesting theorem, lemma, which is actually this function E, actually no eigenvalue, but E in particular can't have a critical point where the eigenspace has dimension 1. Okay, so the critical points where it has dimension 1 are the places we're looking for, but then there's a lemma that says, well, actually, it never has critical points. For example, it can't take on its maximum where the eigenspace has dimension 1. So why is that?
How does that make sense when the number of points is 2? Because didn't we just like say that we could take, there exists a solution with the antipodal.
Yeah,
set?
but those had equal 3 halves. So I'll explain what goes on there, and you'll see what's going on in general. All right, so what happens? So we have a f, which goes like z to the 3 halves near each point. Now, the problem is rotationally invariant. So we can take the generators of the rotation group, which are, rotation around the x-axis, rotation around the y-axis, rotation around the z-axis. These all commute with the Laplacian because everything is rotationally invariant. So if you act by that vector on F, well, you get 3, only 2 of them are linearly independent because there's always rotation. But if you act on that, if F goes to z to the 3 halves, when you act on it by these rotations, or 5 halves, or whatever, you get something which is at worst z to the 1 half. It might be better than that, but it's at worst z to the 1 half. So what that means is, now commutes with the Laplacian. So if the derivative goes like z to the 1 half, that means the derivative by that rotation generator is in your Hilbert space, and it's going to be an eigen vector because it commutes. So anytime it vanishes like z to the 3 halves at all the points, its derivatives will vanish like a power less than z to the 3 halves, which is going to still be a positive power. And so it'll be in your function space, and it'll be an eigenvector. And so in particular, we saw with the antipodal points that we had one which was sine 3 halves theta, and then the real and imaginary parts, so cosine phi over 3 phi over 2, and sine 3 phi over 2. Well, this one turned out to have multiplicity, already have multiplicity 2 because of that other rotation vector. Because that antipodal thing is actually rotationally invariant. In general, if you have more than 2 points, you're never going to get a rotationally invariant configuration. But anyway, it has multiplicity 2, but acting on these other guys, then you have 2 more which go like cosine sine 1 half theta, cos 3 halves. Or maybe it's cos 1 half, I forget. Anyway. And cosine sine. Something like that. I forget if it's 1 half or 3 halves. But anyway, you actually have multiplicity 4, not multiplicity for those. And so it's the rotations say that anytime you would have had a critical point of your function, the multiplicity has to be actually bigger than, it actually has to be probably at least 4. So you're out of luck if you're hoping to get critical points. And actually, so then there's an even kind of stranger theorem, which is that well, we can still look for an eigenfunction f, which goes like z to the 3 halves, and with eigenvalue e, even if it have higher multiplicity, we could still look for that. And then there's a proposition that says they don't exist. Proposition. I think the theorem is that f has to go like z to the 1 half at least. I forget if it's n plus 1 of the 2 endpoints. In P, if it's eigenvalue, if lambda is E, the minimum one. Okay. So that's a little graph theory. So it not only is this minimal eigenvalue not a critical point where it's smooth, it's just not a critical point at all. Okay, so that's kind of a strange thing. How could you have, I mean, obviously it takes on its maximum because it doesn't take on its maximum at the, on the divisors, on the added compactification. So it takes on its maximum, but that maximum actually isn't, the function isn't smooth there, it's just continuous. And in fact, there's no eigenvalue at that place which behaves as if it were a critical point. And so we'd like to explain that. I'd like to explain that, what is going on here. So this is kind of really strange stuff. There's some kind of bizarre spectral flow, which you're taught, you know, you're taught, well, there's no interesting spectral flow for the Laplacian, right? I mean, everybody's taught that. You have to have a Dirac operator to have interesting spectral flow. You know, Laplacian, it's, you know, symmetric operator, nothing can happen. Well, here, there's some really cool spectral flow going on, which I don't understand. We don't understand yet, but it's a kind of a spectral flow that involves a self-adjoint operator and not a Dirac operator. And so what's going on? So let me give you, I have 4 minutes to go, right?
Sure.
So let me spend a minute to tell you actually what's happening. What I think is behind the reason this E isn't actually a critical value. So what you can try to do is construct a Hilbert space bundle over your configuration space whose fiber over P is this Hilbert space where your Laplacian sits. Okay, and then you can think of, inside here you have a unit sphere bundle, which is a set of F's which have integral equal to 1. And so you can restrict this to S, and then over C2n. And then you have a function on here, which is the integral of df squared. And it's really the critical points of that function we're looking at as a function on this total space. And so, well, actually it's invariant under plus or minus 1. So it's actually in a function on the RP space that projectivizes its projective space. And you're looking for critical points of that, because those will be actually, they'll be critical with respect to moving this way, and there'll be critical points with respect to moving in the fiber, so they're exactly what we want. So an interesting point here is well, actually there's no Hilbert space bundle. You can't build a Hilbert space bundle or a sphere bundle over C2n because there's an obstruction. There's a second Stiefel-Whitney class obstruction. You can build an RP bundle, but the RP bundle is not the quotient of an S bundle, a sphere bundle. So there is an RP bundle with fiber projective spaces, and there is this function, which is a nice function on it. So we can look at it as critical points. So we need to know what the topology of this thing is. And so the topology, we look at Z mod 2 cohomology, H star, and we can sort of do min-max, you know, Lusternik-Schnellmann theory, whatever you want to call it, kind of poor man's Morse theory. And, but now we can see exactly what goes wrong with using this E. And what goes wrong is that the fact that this guy doesn't lift, to a sphere bundle is flagged by a class, a two-dimensional class on the base. And this two-dimensional, and because the two-dimensional class of the obstruction, if I call this pi, then the pullback is actually exact. D nu. And one other thing, the product of the two-dimensional class with itself and times is not 0. so that tells us that, and so therefore the pullback of this is exact. If we look at pi star of that, that is exact. It's equal to d of nu wedge omega n minus 1. So if we dualize to homology, that tells us that if we had a fundamental class here, there's no lift of the fundamental class to RP. And, you know, in some, so this isn't a rigorous argument, but if you could, if this E, if you could make sense of this E as a sort of smooth function, you know, with critical points, I mean, E is basically the min-max of a lift of the, trying to be the min-max of a lift of a fundamental class. But there is no lift of a fundamental class because the dual class pulls back at 0. Well, that's really fast, but that's at least some indication that there's some cool stuff going on. And I'll be honest with you, you know, we don't understand it yet, but it seems kind of fun. So I'll stop here. I'm a minute over on my clock. I don't know where you guys are, but.
All right. Well, I know that made me feel like a mathematician by Cliff's definition. Are there questions?
I have a question. So in your construction, is there a way we know like the critical point, like the coefficients of the Z3/2 part doesn't vanishing?
Say it again.
Like in the constructions you made, probably you can guarantee that the coefficients of Z1/2 in front of it is vanishing. But is there a way to guarantee that the coefficient of Z3/2 part non-vanishing for that kind of Z2 functions?
Which part do you want? Not the next order part?
Yeah, the next order part, like it looks like if you have a like only that term doesn't vanishing, you will have a deformation.
Yeah, what happens is in general, F goes like the real part of some complex number, or let me call it beta, times e to the n plus a half, plus higher order terms, where beta is some non-zero complex number, and n is equal to, it can be anything, any integer. So that's the general form. And you know, if you had one with you know, with n equal to 1 for all of them, you could then ask, you know, what is the condition that you have one with n equal 2 for all of them, or something like that. I don't know. Yeah, so I don't know. I don't have a geometric interpretation of that. That's yeah.
Thanks.
N equal 1 are formally the critical points of this function on our space, our projective bundle RP. And so what our goal would be is to understand the Z2 homology cycles well enough to argue that it has critical points that aren't on the compactification.
Okay, thank you.
Hi, Cliff. Thanks for the talk. Just to make sure that I understood the punchline. So the goal is to show that for arbitrary large values of n, you have some singular configuration.
Yeah, right.
In the case that n is in the case that you have 4 points on the sphere,
yeah,
is the tetrahedron the only configuration, or do you have? I mean, is there a possibility?
Yeah, we don't know. We don't have any kind of uniqueness theorem about that. We just know, we found it by just using the symmetries of the tetrahedron, and it could be that's the only case where the 4 points where they're you know symmetric, have this tetrahedral symmetry. It could be there are other 4 points that work also. Yeah, I have no idea.
Okay.
Yeah.
So I was just going to go back to the gauge theory motivation. Is there any, you know, hope that maybe there's some sort of general, some generic metric theorem which says that, you know, for a generic metric you have only the smooth case,
Yeah, sure. That's a great theorem. I wish I could prove it.
Okay.
That would be a wonderful theorem. And I would be delighted to be able to prove that.
But I mean, but the stuff that you're working on is not I mean, it doesn't contradict that, right? So it's not like you can prove that there is no generic metric theorem.
No, I don't think it contradicts it. It gives us some indication of what, it gave me some ideas what I might try to do to prove that theorem. Some kind of analytic approach, but I'm sure that it's nothing I sat down with to show. Presumably, if I sat down with it for 2 hours, I'd see I was being stupid. But it's going the other way and saying, well, we know there are singular configurations. So what? Maybe they're only the ones from the Platonic solids. I mean, I doubt that, but maybe it's the case. Most you have are 12 rays from the origin. That's it. I mean, one could have hoped that there were none except antipodal, and then we wouldn't have had to prove a generic metric theorem. But,
right. Okay, thank you.
Yeah, but a generic metric theorem would be wonderful. I mean, that'd be a great theorem. I mean, I would be delighted to prove that. I would applaud anybody else who proved it. I'd swallow my disappointment that it wasn't me and prove it, and congratulate whoever proved it.
So do you know, have you thought about trying to perturb the tetrahedral solution to a, kind of very smooth C1 curves that?
Yeah, but you expect that these things are isolated. So, of course, it's rotationally invariant, so any rotation of tetrahedron gives you. But aside from that, aside from the rotation group, you expect them to be just dimension counting. Because it's critical points of a Morse function, you expect them to be isolated.
No, but what I'm asking is that, oh, I see. No, but
so you're thinking of look at the Hessian of these places and see.
No, I mean, what I'm asking is just, so your construction gives you the singular solution where the, you have these 4 arcs that meet at a point in R3.
Yeah.
Right. And then you could ask, maybe you have to perturb the metric to do this, but can you change that to a, can you move that to a?
Actually, so Ryosuke Takahashi was telling me, was working on this idea to do that, to prove that perturbate, that anything that was, if it was singular, so it's a little subtle because these are the limit, the blow up limit isn't known to be unique yet.
Yeah.
So it's a little, but suppose you had a unique blow up limit, which was actually these tetrahedral thing, some number of rays. Ryosuke was, so there's a way you could approach it. Sorry. There's a way you could approach it, which is that redo Ryosuke's thing. But, so formally you would want to redo Ryosuke's thing with the constraint that there are, 4 rays or 8 rays or whatever. And then prove that the index of that, was negative. So he showed that there's a kind of moduli space of these things, which are functions, moduli space of metrics and z's and harmonic forms. And if you could show that, if you can redo his thing where things, come together as rays, which I'm sure you could do. And he said he sort of had it worked out last time I talked to him, but I haven't seen any paper or anything, so I don't know if he ran into problems at this point. But if you could show that the index was negative by putting these constraints that it has to come together as rays, that would show, that would be a generic. It wouldn't be a complete generic metric theorem because the singularities aren't known to be, that regular, that sort of.
Yeah.
But assuming if you could show that there was a unique tangent cone to the singular locus, then that might, maybe Ryosuke's proof would go over and actually prove generically there wasn't any singularity. So Ryasuga, and actually, this is sort of, I guess Simon wrote up, a more general version of that for any dimension, everything. But, if you just assume that the singular locus is a submanifold, then you can show that the deformation problem, where you change the metric and change the singular locus and change the harmonic one form or spinor, that's a Fredholm, it has a Kurnishi picture, and it's the usual picture, right? And the index is I forget, is 0, at least in dimension 3. But for the harmonic one forms anyway, 0 or minus, anyway, they don't deform away. But now you redo that analysis where you have a singularity, a bunch of rays, which, that's of course a little bit more complicated analysis, but you should be able to do that. And then you see if the index is gets more negative, the more rays you add, you expect it to do that. And so that would go a long way to, you still have to prove a stronger regularity theorem than we have now, but that regularity theorem seems reasonably likely. Or maybe you could get it to work even in the sort of case where you don't have unique tangent. Yeah, I don't know. But
are there further questions? It is kind of nice to see everybody, even if it's not in person.
yeah, it's actually a pleasure to see everybody.
Do my part.
Who's here? All these people I know. Oh my God. We should have some big party when everybody gets vaccinated. They're totally blitzed.
Yeah.
Everybody has to give a math talk while they're totally drunk. Really fascinating. The best conference there ever was.